Section 6 of Passages from the Life of a Philosopher. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Passages from the Life of a Philosopher by Charles Babbage. Section 6. Difference Engine Number 1. Part 2. Triangular Numbers. Perhaps my young friend may now ask me, what is the use of such tables? Until he has advanced further in his arithmetical studies, he must take for granted that they are of some use. The very table about which he has been reasoning possesses a special name. It is called a table of triangular numbers. Almost every general collection of tables hitherto published contains portions of it of more or less extent. Above a century ago, a volume in small quarto containing the first 20,000 triangular numbers was published at The Hague by E. de Joncourt, A.M., and professor of philosophy. I cannot resist quoting the author's enthusiastic expression of the happiness he enjoyed in composing his celebrated work. Quote, "The trigonals here to be found, and nowhere else, are exactly elaborate. Let the candid reader make the best of these numbers, and feel, if possible, in perusing my work the pleasures I had in composing it. The sweet joy may arise from such contemplations cannot be denied. Numbers and lines have many charms, unseen by vulgar eyes, and only discovered to the unwearied and respectful sons of art. In features the serpentine line, who starts not at the name, produces beauty and love, and in numbers, high powers and humble roots give soft delight. Lo, the raptured arithmetician, easily satisfied, he asks no Brussels lace, nor a coach and six. To calculate contents his liveliest desires, and obedient numbers are within his reach." Unquote. Square numbers. I hope my young friend is acquainted with the fact that the product of any number multiplied by itself is called the square of that number. Thus, 36 is the product of 6 multiplied by 6, and 36 is called the square of 6. I would now recommend him to examine the series of square numbers 1, 4, 9, 16, 25, 36, 49, 64, etc., and to make for his own instruction the series of their first and second differences, and then to apply to it the same reasoning which has been already applied to the table of triangular numbers. Cannon balls. When he feels that he has mastered that table, I shall be happy to accompany Mamma's darling to Woolwich or to Portsmouth, where he will find some practical illustrations of the use of his newly acquired numbers. He will find scattered about in the arsenal various heaps of cannon balls, some of them triangular, others square or oblong pyramids. Looking on the simplest form, the triangular pyramid, he will observe that it exactly represents his own heaps of marbles, placed each successively, one above another, until the top of the pyramid contains only a single ball. The new series thus formed by the addition of his own triangular numbers is represented in a table where the first row contains the number 1, the table 1, the first difference of 3, the second difference of 3, and the third difference of 1. In the second row the number is 2, the table is 4, the first difference is 6, the second difference is 4, the third difference is 1. In the third row the number is 3, the table is 10, the first difference is 10, the second difference is 5, the third difference is 1. In the fourth row, the number is 4. The table is 20. The first difference is 15. The second difference is 6. In the fifth row, the number is 5. The table is 35. The first difference is 21. In the sixth row, the table is 56. He will at once perceive that this table of the number of cannonballs contained in a triangular pyramid can be carried to any extent by simply adding successive differences, the third of which is constant. The next step will naturally be to inquire how any number in this table can be calculated by itself. A little consideration will lead him to a fair guess. A little industry will enable him to confirm his conjecture. Number in each pile. It will be observed at page 49 that in order to find independently any number of the table of the price of butcher's meat, the following rule was observed. Take the number whose tabular number is required, multiply it by the first difference. The product is equal to the required tabular number. Again, at page 53, the rule for finding any triangular number was, take the number of the group, 5, add 1 to this number, it becomes 6, multiply these two numbers together, 30, divide the product by 2, 15. This is the number of marbles in the fifth group. Now let us make a bold conjecture respecting the table of cannonballs, and try this rule. Take the number whose tabular number is required, say 5. Add 1 to that number, 6. Add 1 more to that number, 7. Multiply all three numbers together, 210. Divide by 2, 105. The real number in the fifth pyramid is 35. But the number 105 at which we have arrived is exactly 3 times as great. If, therefore, instead of dividing by 2, we had divided by 2 and also by 3, we should have arrived at a true result in this instance. The amended rule is therefore, take the number whose tabular number is required, say n. Add 1 to it, n plus 1. Add 1 to this, n plus 2. Multiply these three numbers together, n times n plus 1 times n plus 2. Divide by 1, by 2, by 3. The result is n times n plus 1 times n plus 2 divided by 6. This rule will, upon trial, be found to give correctly every tabular number. By similar reasoning, we might arrive at the knowledge of the number of cannonballs in square and rectangular pyramids. But it is presumed that enough has been stated to enable the reader to form some general notion of the method of calculating arithmetical tables by differences which are constant. Astronomical tables. It may now be stated that mathematicians have discovered that all the tables most important for practical purposes, such as those relating to astronomy and navigation, can, although they may not possess any constant differences, still be calculated in detached portions by that method. Hence the importance of having machinery to calculate by differences, which, if well made, cannot err, and which, if carelessly set, presents in the last term it calculates the power of verification of every antecedent term. Of the mechanical arrangements necessary for computing tables by the method of differences. From the preceding explanation, it appears that all tables may be calculated to a greater or less extent by the method of differences. That method requires, for its successful execution, little beyond mechanical means of performing the arithmetical operation of addition. Subtraction can, by the aid of a well-known artifice, be converted into addition. Addition. The process of addition includes two distinct parts. First, The first consists of the addition of any one digit to another digit. The second consists in carrying the tens to the next digit above. Let us take the case of the addition of the two following numbers in which no carriages occur. 6023 plus 1970 equals 7993. It will be observed that in making this addition the mind acts by successive steps. The person adding says to himself, 0 and 3 makes 3, 7 and 2 make 9, 9 and 0 make 9, 1 and 6 make 7. Carriage. In the following addition there are several carriages. 2648 plus 4564 equals 7212. The person adding says to himself, 4 plus 8 makes 12. Put down 2 and carry 1. 1 and 6 are 7, and 4 makes 11. Put down 1 and carry 1. 1 and 5 are 6, and 6 make 12. Put down 2 and carry 1. 1 and 4 are 5, and 2 make 7. Put down 7. Now, the length of time required for adding one number to another is mainly dependent upon the number of figures to be added. If we could tell the average time required by the mind to add two figures together, the time required for adding any given number of figures to another equal number would be found by multiplying that average time by the number of digits in either number. When we attempt to perform such additions by machinery, we might follow exactly the usual process of the human mind. In that case, we might take a series of wheels, each having marked on its edges the digits 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. These wheels might be placed above each other upon an axis. The lowest would indicate the units figure, the next above the tens, and so on, as in the difference engine at the exhibition, a woodcut of which faces the title page. Several such axes, with their figure wheels, might be placed around a system of central wheels, with which the wheels of any one or more axes might at times be made to gear. Thus the figures of any one axis might, by means of those central wheels, be added to the figure wheels of any other axis. But it may fairly be expected, and it is indeed of great importance, the calculations made by machinery should not merely be exact, but that they should be done in a much shorter time than those performed by the human mind. Suppose there were no tens to carry, as in the first of the two cases. Then, if we possessed mechanism capable of adding any one digit to any other in the unit's place of figures, a similar mechanism might be placed above it to add to the tens figures, and so on for as many figures as might be required. But in this case, since there are no carriages, each digit might be added to its corresponding digit at the same time. Thus, the time of adding by means of mechanism any two numbers, however many figures they might consist of, would not exceed that of adding a single digit to another digit. If this could be accomplished, it would render additions and subtractions with numbers having 10, 20, 50, or any number of figures as rapid as those operations are with single figures. Successive carriage. Let us now examine the case in which there were several carriages. Its successive stages may be better explained thus. Stages: 2648 plus 4584 equals 2642. 1. Add units. Figure equals 4. 2. Carry 1. 3. Add tens figures equals 8. 2632. Carry the 1. 2732. Add hundreds figures equals 5. 2232. Carry the 1. 3232. Add thousands figures, which is 4. 7232. Carry 0. There is no carriage. Now, if, as in this case, all the carriages were known, it would then be possible to make all the additions of digits at the same time, provided we could also record each carriage as it became due. We might then complete the addition by adding, at the same instant, each carriage in its proper place. The process would then stand thus. Stages: 2648 plus 4564. 6102. Add each digit to the digit above. 111. Record the carriages. 7212. Add the above carriages. Now, whatever mechanism is contrived for adding any one digit to any other must, of course, be able to add the largest digit, 9, to that other digit. Supposing, therefore, one unit of number to be passed over in 1 second of time, it is evident that any number of pairs of digits may be added together in 9 seconds, and that, when all the consequent carriages are known, as in the above case, it will cost 1 second more to make those carriages. Thus, addition and carriage would be completed in 10 seconds, even though the numbers consisted each of 100 figures. But unfortunately, there are multitudes of cases in which the carriages that become due are only known in successive periods of time. As an example, add together the two following numbers, 8473 and 1528. Add all the digits, 9991. Carry on tens and warn the next carriage, 19901. Carry on hundreds and ditto, 9001. Carry on thousands and ditto, 00001. Carry on 10,000s, 10001. In this case, the carriages only become known successively, and they amount to the number of figures to be added. Consequently, the mere addition of two numbers, each of 50 places of figures, would require only 9 seconds of time, whilst the possible carriages would consume 50 seconds. The mechanical means I employed to make these carriages bears some slight analogy to the operation of the faculty of memory. A toothed wheel had the 10 digits marked upon its edge. Between the 9 and the 0 a projecting tooth was placed. Whenever any wheel in receiving addition passed from 9 to 0, the projecting tooth pushed over a certain lever. Thus, as soon as the 9 seconds of time required for addition were ended, every carriage which had become due was indicated by the altered position of its lever. An arm now went round which was so contrived that the act of replacing that lever caused the carriage which its position indicated to be made to the next figure above. But this figure might be a 9, in which case, in passing to 0, it would put over its lever, and so on. By placing the arms spirally round an axis, these successive carriages were accomplished. Multitudes of contrivances were designed, and almost endless drawings made for the purposes of economizing the time and simplifying the mechanism of carriage. In that portion of the difference engine in the exhibition of 1862, the time of carriage has been reduced to about 1/4 part of what was at first required. Anticipating carriage. At last, having exhausted, during years of labor, the principle of successive carriages, it occurred to me that it might be possible to teach mechanism to accomplish other mental processes, namely, to foresee. This idea occurred to me in October of 1834. It cost me much thought, but the principle was arrived at in a short time. As soon as that was attained, the next step was to teach the mechanism which could foresee to act upon that foresight. This was not so difficult. Certain mechanical means were soon devised which, although very far from simple, were yet sufficient to demonstrate the possibility of constructing such machinery. The process of simplifying this form of carriage occupied me at intervals during a long series of years. The demands of the analytical engine for the mechanical execution of arithmetical operations were of the most extensive kind. The multitude of similar parts required by the analytical engine, amounting in some instances to upwards of 50,000, rendered any, even the simplest improvement of each part a matter of the highest importance, more especially as regarded the diminished amount of expenditure for its construction. Description of the existing portion of difference engine number 1. That portion of difference engine number 1, which during the last 20 years has been in the Museum of King's College at Somerset House, is represented in the woodcut opposite the title page. It consists of 3 columns, each column containing 6 cages. Each cage contains 1 figure wheel. The column on the right hand has its lowest figure wheel covered by a shade, which is never removed, and to which the reader's attention need not be directed. The figure wheel next above may be placed by hand at any one of the 10 digits. In the woodcut it stands at 0. The third, fourth, and fifth cages are exactly the same as the second. The 6th cage contains exactly the same as the 4 just described. It also contains 2 other figure wheels, with which a similar one above the frame may also be dismissed from the reader's attention. Those wheels are entirely unconnected with the moving part of the engine and are only used for memoranda. It appears, therefore, that there are in the first column on the right hand 5 figure wheels, each of which may be set by hand to any of the figures 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. The lowest of these figure wheels represents the units of any number, the next above the tens figure, and so on. The highest figure wheel will therefore represent tens of thousands. Now, as each of these figure wheels may be set by hand to any digit, it is possible to place on the first column any number up to 99999. It is on these wheels that the table to be calculated by the engine is expressed. This column is called the table column, and the axis of the wheels is the table axis. The second or middle column has also 6 cages, in each of which a figure wheel is placed. It will be observed that in the lowest cage the figure on the wheel is concealed by a shade. It may therefore be dismissed from the attention. The 5 other figure wheels are exactly like the figure wheels on the table axis and can also represent any number up to 99999. This column is called the first difference column, and the axis is called the first difference axis. The third column, which is that on the left hand, has also 6 cages, in each of which is a figure wheel capable of being set by hand to any digit. The mechanism is so contrived that whenever may be the numbers placed respectively on the figure wheels of each of the 3 columns, the following succession of operations will take place as long as the handle is moved. First, whatever number is found upon the column of first differences will be added to the number found upon the table column. Second, the same first difference remaining upon its own column, the number found upon the column of second differences will be added to that first difference. It appears, therefore, that with this small portion of the engine any table may be computed by the method of differences, provided neither the table itself nor its first and second differences exceed 5 places of figures. If the whole engine had been completed, it would have had 6 orders of differences, each of 20 places of figures, whilst the 3 first columns would each have had half a dozen additional figures. This is the simplest explanation of that portion of the difference engine number 1 at the exhibition of 1862. There are, however, certain modifications in this fragment which render its exhibition more instructive, and which even give a mechanical insight into those higher powers with which I have endowed it in its completed state. As a matter of convenience in exhibiting it, there is an arrangement by which the 3 upper figures of the second difference are transformed into a small engine which counts the natural numbers. By this means it can be set to compute any table whose second difference is constant and less than 1,000, whilst at the same time it thus shows the position in the table of each tabular number. In the existing portion, there are 3 bells. They can be respectively ordered to ring when the table, its first differences and its second difference pass from positive to negative. Several weeks after the machine had been placed in my drawing room, a friend came by appointment to test its power of calculating tables. After the engine had computed several tables, I remarked that it was evidently finding the root of a quadratic equation. I therefore set the bells to watch it. After some time the proper bell sounded twice, indicating and giving the 2 positive roots to be 28 and 30. The table thus calculated related to the barometer, and really involved a quadratic equation, although its maker had not previously observed it. I afterwards set the engine to tabulate a formula containing impossible roots, and of course the other bell warned me when it had attained those roots. I had never before used these bells, simply because I did not think the power it thus possessed to be of any practical utility. Again, the lowest cages of the table and of the first difference have been made use of for the purpose of illustrating 3 important faculties of the finished engine. First, the portion exhibited can calculate any table whose third difference is constant and less than 10. Second, it can be used to show how much more rapidly astronomical tables can be calculated in an engine in which there is no constant difference. Third, it can be employed to illustrate those singular laws which might continue to be produced through ages, and yet after an enormous interval of time change into other different laws, each again to exist for ages and then to be superseded by new laws. These views were first proposed in the 9th Bridgewater Treatise. Curious questions. Amongst the various questions which have been asked respecting the difference engine, I will mention a few of the most remarkable. One gentleman addressed me thus: "Pray, Mr. Babbage, can you explain to me in 2 words what is the principle of this machine?" Had the querist possessed a moderate acquaintance with mathematics, I might in 4 words have conveyed to him the required information by answering the method of differences. The question might have indeed been answered with 6 characters, thus: delta to the 7th power times u sub x equals 0. But such information would have been unintelligible to such inquirers. On 2 occasions I have been asked, "Pray, Mr. Babbage, if you put into the machine wrong figures, will the right answers come out?" In one case a member of the upper, and in another a member of the lower house, put this question. I am not able rightly to apprehend the kind of confusion of ideas that could provoke such a question. I did, however, explain the following property, which might in some measure approach towards an answer to it. It is possible to construct the analytical engine in such a manner that after the question is once communicated to the engine, it may be stopped at any turn of the handle and set on again as often as may be desired. At each stoppage, every figure wheel throughout the engine, which is capable of being moved without breaking, may be moved onto any other digit. Yet after each of these apparent falsifications, the engine will be found to make the next calculation with perfect truth. The explanation is very simple, and the property itself useless. The whole of the mechanism ought, of course, to be enclosed in glass and kept under lock and key, in which case the mechanism necessary to give it the property alluded to would be useless. End of section 6.